Welcome, everybody. Welcome to Cryptography. This is going to be the very first lecture on cryptography. So I'm really excited about teaching this class. I spent a whole lot of time preparing it, and I'm very much looking forward to working with you. So for this very first introductory lecture, there's so much material to cover that I decided to split the very first class, into two parts. So we have a lecture 1A and 1B, and both are about basic concepts and introductory concepts of cryptography. So the topics in this first part is what is cryptography, the general communication pattern, encryption, decryption, and keys, and a few historical ciphers. So what is cryptography? When you look it up on Wikipedia, you will find that cryptography is defined as the practice and study of techniques for secure communication. So the emphasis here is on, obviously, secure communication. Please note that this is not necessarily a complete picture, because we may want to also secure information that is basically static, sitting on a hard drive, and we may want to make sure that nobody can get access to those kinds of information. So for our purposes, for this class, we basically pretty much only deal with communication, so information that is in flow. So cryptography, the word comes from ancient Greek. It's a hybrid, it's a concatenation of two different things: crypto, which means hidden or secret, and graphy, which means write. So we basically write information and nobody can understand what we are writing. So now let's see what the context of cryptography is, what related areas are. So it turns out that cryptography is a subfield of the big field of cybersecurity. So this is what you're going to study if you are in the cybersecurity program, and it has a whole lot of different topic areas. And one is, of course, network security. And the area that cryptography is related to is cryptology. So cryptology basically is comprises cryptography as well as cryptanalysis. We are not going to do much with cryptanalysis. So our focus really is on cryptography. And let me real quick comment on how cryptography, what our plans are to teach cryptography here at NAU. So when it comes to cryptography, it's basically two big things. It's the left-hand side part here and the right-hand side part. So what you will find is that our current cryptography classes is about foundations of cryptography. So this is what those three areas are all about: private key cryptography, public key cryptography, and also hashing. So those are foundational algorithms that later on in a second class, which possibly would be called, CYB403, most likely. What we're going to learn there is we are going to learn these foundational algorithms in application contexts. So big keywords here are TSL, transport, layer security, blockchain, and so forth. And these technologies, they all make use of our foundational algorithms that we are going to learn here. So that's the big picture. So think of the left-hand side here being 402 and the right-hand side as 403. The class is not officially on the books, but we can expect that this is going to happen very likely soon. Okay. Okay. So what is the general communication pattern? I said for the purposes of our class, mostly we will look at information and how to secure information that is in flow. So the thing is that you know, the internet, which is basically our model medium that we look at when it comes to transmitting information over a network, it's inherently insecure. So in principle, anybody like Oscar could get access to this insecure channel. We normally have two parties who try to communicate with each other, and for our class, we will call them Alice and Bob. So Alice wants to communicate with Bob, and she wants to have a secure communication over this inherently insecure channel. And there's always the chance that Oscar comes in. Sometimes Oscar is also called Eve, possibly from evil. So Oscar comes in and may do a number of things to this insecure channel. The easiest would be to just listen and try to figure out what these pieces of information that go back and forth, what it is all about. Oscar, however, may take a more active role actually and change information or just act as the other partner in that communication. So there are different levels of severity how attacks can be done by Oscar on an ongoing communication between Alice and Bob. So that's the basic picture. So where comes encryption and decryption and keys? Where do all this comes in? Well, from the above, we have seen that we need to secure the flow of information over this inherently insecure channel. So basically, the approach is that we have our plain text, and we, for the purposes of our class, we call the plain text X. We have to encrypt that plain text by way of an algorithm that obfuscates the information and basically transfers maps X into a ciphertext Y. And the algorithm that is actually doing that we call encryption, and this is part of the cipher you know, that helps us to encrypt and decrypt the information. So a big part, an important part is in this picture is that we have a key. So while the cipher, so E or D, is actually known how it works, what makes it hard for an attacker to figure out what an encrypted text actually means is actually a secret that is being thrown in, and we call that secret a key. So you see, what we do is on the sender side, we apply the encryption cipher on the plain text, and we get a encrypted text, and we put a secret in there so that somebody trying to attack and try to understand what Y means actually will be unsuccessful. And on Bob's side, that ciphertext is being translated back into the plain text by way of a decryption algorithm, which is the second part of the cipher. So mind that cryptology, cryptography, encryption, decryption is all spelled with Y's, while cipher is not. Okay, so can I get rid of that here? All right, so that said, we have two parts. We have the secret, the key, and the number of possible keys in a certain mathematical, scheme, a certain cipher. We call that the key space. And then we have the algorithm that is doing the encryption and the decryption, and we call that the cipher. So now in modern cryptography, and I emphasize in modern cryptography, the cipher algorithm is actually open. Everybody can look up how modern ciphers work, how things are being computed, how the encryption and decryption algorithm is being employed or deployed. So this comes as a surprise, and in ancient history, ciphers were never open; they were kept as a secret. So, in contrast to the cipher, of course, the key is secret. Okay. So the question comes up: why is the cipher open? Why can everybody, know what the cipher is and how it works? So why do we publish the cipher? Okay. The reason is that publishing the cipher makes it actually more secure. And it increases the trust in the cipher. Why is that? Well, just imagine that you do not publish a cipher. So if you keep it a secret, if you keep your cipher a secret, somebody else may still figure it out and not tell you, that the cipher basically has been broken, and all of the messages that you deem secret and safely encrypted can be decrypted, and you don't even know about it. Actually, there is historical evidence for things like that, that things like that have happened. And the most recent one is World War II, where the German Enigma was figured out, and other decryption and encryption machines, by the way. Enigma was not the only one. And it was figured out by the British, and really, really important messages about the plans of attacks and stuff that the Germans sent back and forth could be decrypted, understood, and acted accordingly. And historians think that this was a big part for the Germans to eventually get defeated. So if you, on the other hand, if you open up the cipher, let everybody know what it is, the whole community will have a chance to actually test the cipher and report weaknesses of the cipher. And, that leads to conclusions as to how safe a cipher is. And this is a way more secure way of going about ciphers. So a few recent examples are the DES algorithm, which is a block cipher. It was found that this algorithm is not secure anymore, and it has been replaced by AES that we are going to cover in this class. So that perspective of modern cryptography, those foundational principles to keep the key the secret, but keep the algorithm and most likely the mathematical algorithm, how to encrypt and decrypt open, that has already been developed in 1883 by Kerckhoffs. So Kerckhoffs is a Dutch cryptographer and linguist who laid out that the cipher itself should not be a secret, and it should not be a problem if the cipher itself falls into the hands of an enemy. So exactly what I just commented on. This was developed by Kerckhoffs and is one of those principles that he laid out in 1883. So other issues that should be considered, that are closely interrelated actually, are confidentiality. So this is basically what we talked about above. It's actually hiding the content of a message. So if you get a message and you decrypt it, you should be totally trusting the content of the message. Nobody else actually saw it. The question, however, is who is that message from, and what about the message integrity? So two other aspects are, when we talk about message integrity, is the message that you received actually the original message, or did it get tampered with, either totally be replaced by Oscar or changed? So that's still the question. So apart from confidentiality, that confidentiality may only be existing between Bob and Oscar. If the message, got intercepted by Oscar and resent to Bob, for instance. So in this case, we actually do have confidentiality, but we have the wrong sender. So how do we know that the message is actually that we receive from the party that we were expecting it to receive from? So sender authentication and message integrity are two other different and important aspects of encryption, decryption that we need to consider. Okay, so that leads us to the next topic, which is historical ciphers. So keep in mind that historically, ciphers have been kept secret, and this is especially true for Caesar's cipher, which is a substitution cipher. Substitution means that letters are being replaced according to some scheme, one by one. So in case of the Caesar's cipher, letters were just basically shifted related to their position in the alphabet by 3 positions. Okay, so here's an example. By the way, here's a link where you can, look up Caesar's cipher as well as other historical ciphers. So you see how that works here in the picture. If we have the letter A, and the letter A appears in the plain text and needs to be encrypted, it's going to be replaced by a letter that is 3 positions further down in the alphabet. Okay, so in other words, out of A becomes D, and out of B becomes E, and so forth. So, of course, this is an incredibly weak cipher, and it can be easily broken by what is called normally frequency analysis. So frequency analysis is one of the most basic cryptanalysis techniques. that rely on the idea that the cipher does not really change the frequency of the occurrence of letters. Okay, so what you see is if you have a whole lot of E's, and you know that E's in the English language appear more frequent than other letters, and you have a whole bunch of H's in the ciphertext, most likely the H, is the encrypted version of the letter E. So for any cipher where the frequency of the letters is not changed, they are vulnerable to frequency analysis attacks. Okay, so the next cipher that I would like to introduce is a substitution cipher as well. And believe it or not, when I was a kid of maybe 7, 8 years, my grandmother taught me this cipher. It's a really true story. And I have never in my whole life, and I'm 63 now, I have never ever heard about that cipher again in my life, just that one time from my grandma. So it's a thing that they did, when they were kids, and I was totally excited about that cipher, and I encrypted all kinds of messages back then. And hardly I would have been really, really surprised back then if somebody would have told me, that I would become professor for computer science and actually have the responsibility to prepare a cryptography class. It's just amazing how life plays out. Anyhow, so and you are actually the very first audience that I'm explaining that cipher to. So the cipher actually consists of a magic formula, and in German you would call it ma, le, fi, so, hu. And that formula maps actually letters. So if you want to encrypt a certain letter, you just go into that formula like the letter M, okay? And you replace that letter with the other letter in the pair of the two letters. So that's the idea. If a letter doesn't appear at all, what you do is you just you transfer it. It's being transferred through as it is. So letter X is not here. So if you have to encrypt letter X, it would actually not be encrypted. Or letter Y would, be the same. Z would be the same. C, and so on. So that's how the decryption, works the very same way. So you would take a letter, you would go into that formula. If the letter is there, you would replace it with the other letter in the pair that it is part of. And if a letter is not appearing there, you just write it down as it is. So let's get to an example. This is an encrypted word. So what does it mean? So you go letter by letter. So go with the G first. Is the G here? No, it's not. So you just, write down the G as it is. So then we have the L. The L is here, so we replace it with the E. And you get the idea. So the U is replaced by an H, the L is replaced by an E, the F is replaced by an I, then the A is replaced by an M, and then we have an N, which is not appearing in the formula. We have an F, which is an I, and we have the O, which is an S. So the whole word reads Geheimnis, which is actually the German word for secret. Okay. Secret. All right. So what you see is that we have a partial mapping of characters. We actually have a 100% mapping of vowels because all of the vowels are there, but only a partial mapping of consonants. Okay, so all of the ciphers that we have looked at so far, Caesar cipher, just the one, you know, and the second one, my grandmother's cipher, those are called monoalphabetic ciphers. And they are called that because each letter has a firm, you know, mapping to another letter, and that's it. That's just what it is. So convince yourself that my grandmother's cipher is also vulnerable to frequency analysis, because the cipher does not really change the frequency of the appearance of letters. So you may make conclusions if a letter in the ciphertext appears much more often than another letter, then it's one of the letters that appear very often in the English language. Similar if you have German letters, you know, other letters possibly are more frequent than some. Anyhow, so monoalphabetic ciphers. So let me. The ciphertext, the cipher alphabet for each plain alphabet is fixed. So that's what monoalphabetic ciphers are all about. So just think of a fixed mapping between letters in the plain text to letters in the ciphertext. So the next cipher that I would like to look at is the Vigenère cipher. It's an example of a polyalphabetic substitution cipher. So this is way more interesting than monoalphabetic ciphers. And it's interesting because frequency analysis doesn't work as well anymore. So we have a key, a code, and that code, each letter in the key defines the shift that the plain text letter will see that is in the same position. So it's not just a certain number of shifts in positions in the alphabet for a certain letter. It really depends on the key, how many positions a letter is going to be shifted. So in other words, what that means is that the same letters in the plain text are going to be, or potentially are going to be, encrypted by different letters. So this is more interesting because frequency analysis is hard, if not impossible to do. So it's hard to explain, but really easy to understand if you see an example. So let's assume that we have the key CYB. Okay, guess what? CYB, because I was thinking 402. Anyhow, CYB is our key. So an A in the key doesn't make a shift at all. It does not trigger a shift. So which means that a B in the key shifts by 1 position, a C in the key shifts by 2 positions, and so forth. And what you see here is in our key, which is CYB. For the C, we shift 2 positions. For the Y, we shift 24 positions, and for the B, we shift 1 position. So it depends on the position of the letter that we want to encrypt in relation to the the key. So the key basically repeats all the time over the whole plain text. So let me do that here. So you see, we repeat the key basically almost 3 times, and we want to encrypt the letter whatever. Okay, so the W is shifted by 2 positions. The H is shifted by 24 positions, and the A is shifted by 1 position, and so forth. So what you see is that the letter E here, the letter E, and this letter E, because it ends up with different letters in the key, the E is being shifted by different positions in those 2 occurrences. And this makes the Vigenère algorithm much more robust and basically not vulnerable to attacks that use the frequency analysis. Okay. So the same letter is encoded differently, and this is really the cool thing about it. Okay, so you know, online you will see to make those shiftings, you know, mechanically easier to do. There are tables out there that help you with that. So basically what you do is, like in our example, let's say we want to encode the H here. So the H and the Y, the key is the Y. We don't have the Y in here. Yeah, this is really strange. The table is symmetric, and I don't know why they did not continue here, but it doesn't matter. We can say the Y and the H because it's symmetric. So we have the Y here, we have the H here, and where these 2 coordinates meet, we have the encrypted letter. So we have from the H, we get the F. So that's how we could use that table. Again, it's symmetric, so I don't know why they, I should have downloaded probably another one, why it wasn't continued down here. So it doesn't matter because we are not bound to plain text. Looking up here and key here, we can switch that. Alrighty, so this was our first part of the first lecture, and we stop right here, and I will follow up with the second part of the lecture right after this. Okay, thank you.